Hello, my name is David Schoenwald, and I'm a principal member of the technical staff in the Electric Power Systems Research Department at Sandia National Labs in Albuquerque, New Mexico. This presentation is going to discuss a control design methodology for solid-state transformers to be used as a means of limiting cascading disturbances and thus improve the resilience of the grid to severe events, both human-caused as well as natural disasters. I want to thank my colleagues, Brian Pierre and Karina Munoz Ramos, who made outstanding contributions to this work. And I also want to thank Sandia's Laboratory-Directed Research and Development Office for their support of this project. First, some background. Solid-state transformers are fundamentally different from conventional transformers. Solid-state transformers are essentially a power electronics-based device, whereas conventional transformers are passive devices. Both are very efficient, but conventional transformers can introduce harmonics into the power on the either side of the transformer. They can pass disturbances along, and they have a very large footprint. By contrast, solid-state transformers have the ability to decouple phase and frequency between the two sides, and they can do reactive power control, something that the conventional transformers struggle with. They can do power quality management. They have a reduced footprint, and there's the potential to correct phase imbalances between the two sides. In fact, the concept of DC in the middle is a means in which DC-based, inverter-based resources, such as photovoltaic, can be integrated into the grid more naturally with less induced disturbances to the grid. So because of these advantages, we've hypothesized that solid-state transformers have the potential to prevent or at least reduce cascading failures that arise from severe events, and that would improve grid resilience. So we've developed a methodology for control design to do just that for solid-state transformers. And the first step is to design a very high-level model for the SST. And in this case, since we're only looking at grid-level behavior, it can be approximated very well by a critically damped second-order lag system, as you see there. And then, for a very simple example to present here, we looked at a proportional integral compensator design for the SST. And for the parameters given above in step 1, the control parameters were derived in step 2. And you can see the plots, the open loop plot on the top right and the closed loop response on the bottom right. And compare the open loop response. The closed loop response is a 30% faster rise time while maintaining no overshoot. The next step is to actually evaluate the SST control design compared to a conventional transformer. And this can be done in grid simulations. And for this case, we use PSLF. And the example we looked at is the well-known RTS 96 three-area system with a conventional transformer in the third area. That's the base case. The test case is the same thing, except that conventional transformer is replaced with a solid-state transformer with the design compensator. And two events were simulated: a severe generation trip in the first two areas and a severe load trip in the first two areas. And you see below what the grid level block diagram looks like. So the SST, we believe, is an important step to making the grid more resilient. A design methodology has been presented here. We had a simulation example compared to a base case that had no SST. And what we found in the simulations is that the base case illustrated a very weak connection due to the disturbances, and that caused a lot of load shedding. The base case with an SST, however, had significant improvements. We will look further to optimize strategies and design more robust control.